In the previous video, we did trends, atomic radius, and ionic radius. The trends went in the same direction. It decreased going from left to right, and it increased going down the periodic table. The next three trends are in the opposite direction. So ionization energy, or abbreviated IE, is the energy to remove an electron at the gaseous state. So if I write this in an equation format, we have X, element X, in gas. An electron is removed, so it becomes X plus gas. So it becomes a cation. Ionization energy is endothermic. That means it is positive. In order to remove that electron from the atom, we need to input energy. Prior to this unit, you had a graphing assignment in which you had to plot the ionization energy. And your plot should look very similar to this. In general, as I go across the periodic table from left to right, ionization energy increases. As I go down the periodic table, the ionization energy decreases. There are exceptions on the periodic table, and we are going to do the two main exceptions. So why does ionization energy increase as I go from left to right in a period? Again, the reasoning is the same. There is more protons pulling in the electrons, so there's a stronger attraction, while the electron shielding, or the core electron, remains constant. Since there is an increase in effective nuclear charge, it is harder to remove those valence electrons. As I go down the periodic table, ionization energy decreases for the same reason. It is further away from the nucleus because there is more energy levels, or N, principal quantum number. There is more electron shielding because there are more inner electrons, and there are more electrons, so more electron-electron repulsion. Effective nuclear charge decreases down the periodic table. Since it increases across the period from left to right and decreases down the periodic table diagonally from the metals to the non-metals, it will increase. There are many exceptions to ionization energy, but for this class, you need to know the two main ones. The first exception is between groups 2 and 13. In the general trend, as I go from left to right on the periodic table, ionization energy should increase. However, if you look at group 2 and then you move to group 13, there is a slight decrease. This is due to a difference in sub-energy level. According to Alboff principle from the previous unit, Alboff stated that we must fill the lower energy levels first before we move on to the higher energy level. So when we write the electron configuration, we always fill 1s2 before we move on to the next lowest energy level, which is 2s2. After we fill 2s2, we fill 2p6. After we fill 2p6, we fill 3s2, and then 3p6, and so forth. The last energy level we fill is always the highest energy level. According to Alboff, we must fill the lower energy first. When I look at my periodic table, group 1 and group 2 are the S blocks. You know group 1 is S1, group 2 is S2. Group 13 is where we start the P blocks. So 13 is P1, and group 14 is P2, group 15 is P3, and so forth. So according to Alboff's principle, we always fill S before P in a given energy level. So 2S will always have a lower energy than 2P. The P's are at a higher energy level. It is easier to remove the electron. Therefore, if I look at BE, BE is going to be 2s2, B is going to be 2s2, 2p1. Since B is at P, which is a higher energy level, it is a lot easier to remove than BE, which is at 2s, which is lower. So if I look at magnesium, that is 3s2. Aluminum is 3s2, 3p1. For aluminum, it's a lot easier to remove because 3p is at a higher energy level than magnesium, which is at 3s. As we move down the periodic table, you will notice the difference is even smaller because starting period 4 or energy level 4, we fill 4s2 and then we fill 3d10 and then 4p6. So the 3d10s do extra shielding. And then as we move even further down, if you notice, it just follows the trend again. So for group 2 and 13, the reason group 13 has a lower ionization energy than group 2 is because P is at a higher energy level than S. The second exception you need to note is between groups 15 to 16. Ionization energy in general, as you go across, ionization energy increases. However, between 15 and 16, there is a decrease. Unlike the previous exception, we cannot discuss there's a difference in energy level because they are all located in the P block. So what is causing this difference? So they're all located in the P block. So what I'm going to do is I'm going to draw my orbital diagrams. So if I write my electron configuration for nitrogen, that's going to be 2s2, 2p3, and for oxygen it's going to be 2s2, 2p4. For both nitrogen and oxygen, the highest energy level is in the sub-energy level P block. We can't compare the difference in energy level. So what we're going to do is we're going to draw an orbital diagram. P's have 3 orbitals, and according to Hund's rule, we must put 1 electron per orbital before we start pairing to minimize electron-electron repulsion. Since nitrogen has 3, I'm going to start with 1, 2, 3. So that is the 2p3 for nitrogen. For oxygen, again, I'm going to follow Hund's rule. 1 per orbital before I pair. Since oxygen has 4, I need to put an electron in the opposite direction according to Pauli's principle. This paired electron causes electron-electron repulsion, making it easier to remove the electron. This is why the ionization energy of oxygen is lower than nitrogen, because of this one paired electron. So this is true for every single element. So we could say the same thing for phosphorus and sulfur. For phosphorus is 3p3, which is the last energy level, and for sulfur is 3p4. Have 3 orbitals. Hund's rule says 1 electron per orbital before pairing. For phosphorus, it's complete. For sulfur, I'm going to do the same thing, Hund's rule, 1 per orbital, but it needs 1 more electron, so I come back and pair in the opposite direction. This pair of electrons causes electron-electron repulsion, making it easier to remove the electron from sulfur than phosphorus. This is why sulfur has a lower ionization energy than phosphorus. At row 4, 5, and 6, the difference is much smaller, or the exception does not apply. It follows the general trend. But we are not going to do all the exceptions. You need to note the difference between 2 and 13 and 15 and 16. Pause the video, rank the following ionization energy in decreasing order, and then check your answer. Just like atomic radius and ionic radius, we're going to determine, are they in the same period or are they in the same family? If not, find a commonality. So we're ranking these following in decreasing order, so that means we have to go from large or big to small. So if I look at S, P, O, they are in the same family. So we know ionization energy increases going up the family or decreases going down. So the one with the highest ionization energy, because if we're doing large, is going to be oxygen. Then it's going to be sulfur. And then it's going to be polonium. For B, we have carbon, lithium, nitrogen, fluorine, and oxygen. These are in the same period. Ionization increases going from left to right on a periodic table. So we need to rank these in order from right to left. So my biggest one should be fluorine, and then oxygen, nitrogen, carbon, and then lithium. If we follow the general trend. However, oxygen is in group 16 and nitrogen is in group 15 because oxygen has a pair of electrons. There's electron repulsion, so nitrogen is going to be larger than oxygen. So it's FNOCli. For C, we have barium, magnesium, phosphorus, and fluorine. Again, determine if they're in the same period or family. If not, what is the commonality? So we know magnesium and barium are in the same family. So as I go down the periodic table, ionization energy decreases. So what we want to do is go in the opposite direction. So we know magnesium is going to have a higher ionization energy than barium. And then if I look at my periodic table, magnesium and phosphorus are in the same period. So as I go across, ionization energy increases. So I know phosphorus is going to have a larger ionization energy than magnesium, and since fluorine is in period 2, it's going to have the greatest. The best way to do this one is diagonally. Ionization increases on the periodic table. On D, we have rubidium, cesium, helium, hydrogen, and sodium. Most of these are in the same family, so I'm going to rank them by family. And as I go up the periodic table, it is higher in ionization energy. So that tells you hydrogen is going to be the largest, followed by sodium, followed by rubidium, followed by cesium. Helium and hydrogen are in the same row or period. And as I go across, ionization energy increases, so that means helium is going to have a higher ionization energy than hydrogen. So the steps to identifying these are the same. Find the period. If they're not in the same period, determine if they're in the same family. If they're not in the same family, determine if they have a commonality. In general, as it goes from francium to helium, ionization energy increases. And again, note the exception. The exceptions are from groups 2 and 13. This is because there is a change from the S block to the P block. P block is at a higher energy level than S blocks. And then the other exception is 15 and 16. They are in the same block. The difference is when you draw the orbital diagram, group 16 has a pair electron, and due to electron-electron repulsion, it is easier to remove. Therefore, it has a lower ionization energy. And these are the two exceptions that we will be doing in class. In general, you could remove multiple electrons from an atom. As we remove more and more electron, it gets harder. Therefore, the ionization energy increases. As we get closer to the nucleus by changing energy level, the ionization energy that is required to move the electron increases dramatically. IE1 represents the energy to remove the first electron. IE2 is the energy to remove the second electron from that particular atom, which is now an ion. IE3 is the energy to remove the third electron from the ion. And IE4 is the energy to remove the fourth electron. And again, we could go to IE5, IE6, IE7, and so forth. What's going to happen is as we remove more and more electron, it's just going to have a greater ionization energy because the number of protons remain the same. However, there's less and less electrons. Protons are going to attract the electrons even more. So you are given 6 ionization energy. From this 6 ionization energies, you need to determine which family this element can belong to. From the previous chapter, we learned that when we fill, we follow the all-above principle. However, when we remove electrons, this is a review, when we remove electrons, we always remove from the highest end first, which is the energy level, and then the highest sub-energy level in which F is greater than D, and then P, and then S. So we always remove from the highest end. If I look at the 6 ionization energies provided for the 6 electrons, in general, it increases like it should. As I remove more electrons, it's going to be harder and harder to remove the next electron. Ionization energy needs to increase. It doesn't matter which energy level you fill because you always know the energy level S and P are in the same period, and those are my valence electrons. So I'm going to pick an energy level. I'm going to say 3s2, and then I know it's going to be 3p6. So if I remove my first electron, it's going to be from P6. Why? The ends are the same, so I go to the next highest sub-energy level, which is P. If I remove the second electron, so after I remove the first electron, it becomes 3s2, 3p5. So I remove my second electron from 3p5. So now the configuration becomes 3s2, 3p4. I remove my third electron from 3p4. So that becomes 3s2, 3p3. So this is my fourth electron. I remove my fourth electron from 3p3. So that becomes 3s2, 3p2. If I remove my fifth electron, it is still from the p orbital. So that does not account for the big discrepancy that we have, that is over 31,000 kilojoules per mole. So we know this element does not belong in the noble gas family. So that means this discrepancy means there is a change in energy level. So in order to change the energy level, we know that there must be 4 valence electrons, because the 5th electron is where the big jump happens. The 4 valence electron has to be in the carbon family. So that's going to be 3s2, 3p2. Because the carbon family is located right here. So the first electron is going to be removed from 3p2. So if I write the electron configuration, it's 3p1. The second electron is going to be removed from 3p. So now the configuration becomes 3s2. The third electron is removed from 3s2. So the configuration becomes 3s1, 2. The fourth electron is removed from 3s1. Now we are at 2p6. This difference in energy level of a 3 and a 2 is what causes this big jump in ionization energy. So this is my 5th electron, which I'm removing from 2p6. So this element belongs in the carbon family. Pause the video and try this problem on your own, and then check your answer. You're going to figure out which family this element belongs to. Here, 10 ionization energies were given. There is a steady increase until we reach ionization energy 8 and 9. There's a big jump right here. So between 8 and 9, I know that I am going to get closer to the nucleus. So that means 8 of the electrons has to be in the previous energy level, while the 9th one is in the lower energy level. So which family has 8 valence electron? That is the noble gases. If I pick a random energy level with the noble gases, we know that we have to remove from the highest energy level, which is 4. And if there's more than 1, we have to remove it from the highest energy level. Afterwards, if they're in the same energy level, we remove it from the highest sub-energy level. Here it is P. It is 4p. So my first electron is going to be removed from 4p6. My electron configuration becomes 4p5. My second electron is removed from 4p5. This becomes 4s2, 3d10, 3d10, 4p4. So the third electron is going to be removed from 4p4. So now the electron configuration becomes 4s2, 3d10, 4p3. The fourth electron is removed from 4p3. So it becomes 4s2, 3d10, 4p2. We remove the fifth electron from 4p2. So that becomes 4s2, 3d10, 4p1. We remove the sixth electron from 4p1. So this becomes 4s2, 3d10. We're going to move the seventh electron from 4s2 because again it's the highest n. After the highest n, we go to the highest sub-energy level. 4s is still higher than 3d. So this becomes 4s1. The eighth electron is removed from 4s1. So now that means we are at 3p6. Again, there's a change in energy level. And so the ninth one is going to be removed from 3p6. So this one is located in the noble gas. Before the big jump, everything before is the valence electron. So there's 8 valence electrons before it moves down an energy level. In general, for ionization energy, As I go across the periodic table from left to right, it increases. As I go down the periodic table, it decreases. You need to note the 2 exception. It is from group 2 and 13 because it's a change in energy level because the blocks S and P. P is a higher energy level than S. The second exception to the rule that you need to know is between 15 and 16. They are in the same block, P block. However, group 16 has a pair of electrons, and the paired electrons cause electron-electron repulsion, which makes it easier to remove that electron. There are many exceptions to ionization energy, but you will be responsible for the 2 we mentioned in class.